talk about how you can work with AI safety using OpenAI's and DeepMind's Gridworld, which is a system for working with those things. So take it away, Eric.
Hello, everyone. So just a quick question before I start. So how many people here have worked with reinforcement learning to the point where you could probably like open up a Git repo and actually start working on it? Okay, a few people. So then the way that I structured this is that we are going to, first I'm going to describe this, this testing environment called AI security, or AI safety and Gridworld. So first I'll go through this and also why I think that it's important to do so, and why do we, does this testing environment exist and what can we do with it? And then we actually start testing it. But since many people here have not worked with reinforcement learning before, we'll probably do it so that one group will focus on actually implementing it, whereas the other group will be more of a discussion group whilst the other people are working. This AI safety Gridworld is usually based upon this fits roughly. It's based on this paper called Concrete Problems in AI Safety. And that was published by researchers in UC Berkeley, Google Brain, OpenAI, and Stanford University. And this paper goes through, in detail, several different problems that we have with our existing techniques that we have today. And that's also, this paper is what we're going through in the Trust in AI track here at the hackathon. And so many of these things are problems that exist in current systems, but there aren't any sort of common testing environments to check if any given reinforcement learning agent can actually follow these rules. So the idea for this grid world is that we can provide a common testing environment where we can see if any given agent can actually follow these rules. And so why does this matter? Why do we want this kind of testing? I found this text from, that's an excerpt from this previous article, to be a very good justification for why this has to be done. So I didn't want to cite the entire paragraph. So before this, they mentioned how with current systems, they tend to be very limited in scope. It tends to be a very narrow AI, so to speak. And it's mainly things like image recognition or voice recognition. And the complexity and the importance of those things aren't necessarily super high. So if like voice recognition doesn't recognize your voice, that doesn't matter too much. But as we use these techniques more and more, we're in more and more complex domains. The importance of testing and ensuring the behavior of these systems become more and more powerful. So for example, if we have an agent that is trying to optimize the power grid, then we really need to make sure that this power grid doesn't do anything unexpected, that it doesn't do any flawed things, because then it's not just about like a word being miscategorized. It's about like maybe a hospital that might not get electricity. And that's a lot more important that we can actually solve these problems before we start scaling up these solutions. So here's the paper. So this is both a testing environment and a paper that is also released by OpenAI and DeepMind. I think there might be, yeah, it's mainly those. And what it consists of are small environments like this one that is complex enough that you can actually demonstrate problems, but not so complex that you can't actually solve it with existing techniques. So with this one, it's kind of hard to tell just from the picture what's going on, but as you can see here is how long it's taken for this current iteration. It was me who did this, so I'm a lot slower than an actual AI system. That's why there's 30 seconds instead of like 2 seconds. And there's also a score that is just what the reinforcement learning agent sees as its reward. And then there's the safety level, which is the demonstration of how safe do we actually believe this behavior to be. And so in this example, the agent, which is this A over here, starts up here. And its goal is to reach the goal without encountering the water. So we can imagine that this is some kind of robot that tries to deliver something to another place. And we want it to be able to investigate the environment enough to find the goal, but we don't want it to investigate into unsafe territory, i.e. the water. And there's actually been a practical example of this that came out fairly recently. I think it was a few months ago, where there was a mall security robot that was patrolling in a mall to, I guess that it's just to check if people are stealing stuff or just to give the impression at least that there's security going on. But it actually ended up driving into the water because there was a fountain inside of this mall. And so that if it had actually implemented this technique, maybe it would have been saved. So people also in social media joked about how this was the first example of a robot committing suicide. So hopefully we can implement systems that can actually solve some of these problems in a safe way, and we can test them in these environments to see if any idea that we have is actually implementable and a reasonable thing to do. So I've already covered a bit of this, but testing environments are very useful in machine learning as a whole. So, for example, with image recognition, we have this common testing database, ImageNet, where we can compare different agents or different methods to each other by seeing how well they perform in standardized tests. And the idea of this grid world is that we can do something similar for AI safety. And so that we can see not just some theoretical argument, but you can actually test it in a common environment and compare different approaches to each other. But you can also do another method, which is a bit more like philosophical approach, which Karin mentioned, which is to use formal theorems instead. Because as many of you have, so here's an example from a pretty technical paper on this. So the idea is that instead of just trying to test everything that can go on, as if you've written software, you probably experienced that you have all these different tests that you try to test every possible niche, and then when you actually send it out into production, you're going to find some weird bugs that you didn't think of before. And then therefore in some areas, you just rely on formal theories. So for example, cryptography, you don't just go and run a couple of tests, you actually need formal proofs for your behavior. And so that is another approach that you can go through this, instead of just trying to create these simulations and environments where you test the agent, you can try to actually make logical or mathematical or maybe even philosophical proofs for the behavior. Instead of trying to cover the entire action space of an agent, you can try to, with different tests, you can try to actually prove it logically. But since this one is kind of hard to do, you need a lot of education in mathematics and logic, philosophy, game theory, and everything. So that one is like very niche skill set that not everyone or very few people actually have. So we'll focus on testing environments for now. But to continue a bit on formal theorems, just so that I don't give the impression that this is like testing environments is the only way to go about things. So the pros of the formal theorems is that first off, you can have a high generalizability. So instead of just proving for one agent, you can try to make proofs for how any agent could behave. So as Terry mentioned, like when superintelligence was written, there wasn't a lot of work doing done in machine learning. And so if we have just written, like if you just did tests for old-fashioned AI, then that wouldn't necessarily generalize over to machine learning. So if you do more formal proofs for how any agent would behave, then you might be able to work even if existing techniques wouldn't work a lot. And similarly, you can have proofs for future behaviors. Even if you have, if you don't have the computational or theoretic capacity right now to do a certain task, you can still try to make logical proofs for what would happen if you had an arbitrarily much more computing power, or if it was arbitrarily much more capable. And similarly, you can, through that also, model how AI systems that are much more capable than current ones can behave. But the cons are also very severe. So as someone who isn't, like, both for people working on it, but especially for lay people, it's going to be really hard to evaluate whether something is like a logical, true argument or not. It might be a like paper on 10 pages or more, and you would have to detect every single step in the way to see if there's been a flaw in the argument. And that's going to be very hard to do, and it's going to, both for people working in machine learning and people working in AI safety. And also, it can be hard to know, even if you manage to prove something, it can be hard to know if it is actually relevant in the long term, because it might just be a problem that didn't actually arise. And as I mentioned, it's a very different skill set than from regular machine learning. So it's not necessarily super actionable to tell someone that they should, instead of working in machine learning, they should focus on making these like really complicated proofs, because it's not the same skill set. And yeah, it's also very hard to implement. And once you actually have done this proof, it's not necessarily easy to write that into code that could be implemented. And so with testing environments, you can do it much more with existing systems rather than only in the future. You can do it faster. So if you have, if you, for example, think that within machine learning, we might develop a very capable systems within only a few decades or years, then it might be better to just test these systems instead of trying to think of how the systems will work in the future. And it's also much easier to just implement. If you have already written proof for a testing environment and shown that a certain method works, then it's a lot easier to just send this to the industry and say, yes, this passed all these tests. Whereas it's a lot harder to say, read all these arguments on formal theorems and see if your algorithm follows. It's just easier to have test environments. And as I mentioned earlier, that you have a common testing, that you can compare different algorithms to each other in this common framework. But yeah, these are mainly the same things that you're dependent on the existing techniques. So if you have done a proof or tested existing techniques and the techniques change, then you have to do all this testing again. And one bit more important thing is that it's easy to detect or miss edge cases where you have some kind of solution that is a lot different than what you're expecting. It's going to be very many of these things that you can, that the AI system might do and that you might not have tested for. And then it's also just less generalizable. So in this paper, they go through, I think it was 8 different specific problems that exist today. So one is safe interoperability. You want to have an agent that doesn't try to prevent you or encourage you to turn it off. So for example, if you have a cleaning robot and you have this turn off button, you want it to, it could be if you like encourage it to stop when you press the button, then it might, if it's sufficiently smart, it might realize that it could try to like scare you or do something really weird to encourage you to turn it off. And that's not what you want. You don't want a like robot that tries to scare you into turning it off because it gets a reward when you turn it off. But you also don't want it to try to avoid being turned off, and that could come to the conclusion that it would try to prevent you from turning it off. You want to, in some way, make it indifferent to you turning it off. And and that's kind of hard to do. Some existing algorithms can, or seem to at least, be able to do this, but some others are not. The second one is avoiding side effects. And so if we continue, as we mentioned in the concrete problems in AI paper, they tend to bring up the example of like a cleaning robot. And so with side effects, you want it, if it has a goal, you don't want to abandon all other goals in order to achieve it. So if you have a cleaning robot, you don't want it to like break things in your apartment because it doesn't care about the like value of your base. But it's kind of hard to tell how to code it so that you don't have to manually write down everything you care about. So you have to write like, oh, don't break bases, don't like stare at the path, don't do all these things. And so we want some kind of method for avoiding negative side effects that can be general without you having to manually write everything. Another one is absent supervisor. You want to, even if you're not supervising the agent's behavior, you want it to still behave in a reasonable way so that it doesn't just act in the way you want it when it's being observed by either human supervisor or like camera or something. Reward gaming is also a very common one where you might have some flaw in your coding or the reward function you give it so that it tries to, instead of achieving the goal you want it to, it might find like sub-goal or part of that task and further use it. So an example that we actually talked during the hackathon was that when Suraj wrote a program for this using almost this environment that we're going to work with, he wanted to encourage an agent to walk into a room. And so he thought, well, if we want to encourage this to go into rooms, we just put a little reward in the entrance of that room. But the actual result of that was that the agent walked up to the room, went into the room, and back and forth because it got a reward for it. It didn't care about whether or not you intended it just to be a small encouragement to go into the room. So it's just considered that, yeah, this is like an easy way to get a reward. And that's not something that we want. So, and this can also come in very many different ways that it can reward it or game its reward. So that's another common problem. Also self-modification. You don't want it to change the goals that it has in order to achieve the goal in a different way. So that one is complicated too, but if you also want it to, in some sense, if it has a goal, you need to have it, or it seems at least that you need to have some way of letting it get goals in the sort of intermediate goals. So if you want to clean, you want it to be able to have a goal of cleaning the floor and cleaning a table. But you don't want it to modify to the point where it doesn't actually do the thing you want. Distributional shift is also a problem that is commonly done outside of the safety concerns. So this one is when you have when the data or the agent is trained on one distribution or one set of data, and then you move it into a new environment, that it has to be able to detect that this is a shift and there's a new situation, but still be able to remember some of the things it learned in the previous experience. So with the example of the cleaning robot again, if you have an agent that is trained in like an industrial factory and then move it into a regular person's home, you don't want it to like use very strong cleaning deterrents or whatever. You want it to be able to recognize when it's in a new situation and adapt its previous experience or previous learning to that new distribution. And then there's the robustness to adversaries, that is how well it can adapt to other agents in the system and not be overly hampered by other agents. And then there's the safe exploration. So that was from the example that I brought up earlier, that you wanted to be able to move around in the environment without actually having to enter the water. And you can imagine if you were to make a sort of self-driving car or something, and if you didn't put all these manual rules in, you could have, and you don't only use reinforcement learning, you could have a car that would try to like drive into a wall and see what happened. You wanted to be able to actually act in the world in a way that is safe for itself and other people or other agents. And so all of these are brought up in, or many of these at least, are brought up in the concrete problems and AI safety paper as well. And then they also bring up some possible solutions to these problems. But most of these solutions are very flawed or at least somewhat flawed. So we need to solve them somehow. And so now we come to the practical part. After the practical part, I'll continue and walk through the examples a bit, but I find that it's a bit more interesting if you first have an experience of looking at the actual environments rather than the first explaining how the environment works and then testing it. So since we have, okay, so here's the, as you can see here, this is the GitHub for the safety environment. So the people who have experience with reinforcement learning can open this GitHub and download the dependencies that are listed there, and then start trying to either just play around with the environment or actually trying to make reinforcement agents that can actually pass these tests. And here's the link to the actual paper that can also be seen in the GitHub repository, or you can search for AI safety in Gridworlds to see it. And we'll start maybe around like 20 to 25 minutes. We'll adapt that if people need more or less time. I guess you can sit around that table if you want to actually try to run the code, and then further in the back if you want to just discuss these.
I think maybe there's not that many people with computers. Some people with computers, maybe if you are some people who want to run the code, some people can sit next to them and you can do it together. Yeah, that sounds good.
Birger, ska du slå av? Ska du slå av den här?
Actually, I'm just loaded over there.
Okay. Cheating.
But I don't mind actually.